Namaste, I am Kamala Soppin, Assistant Professor of Physics, DRM Science College, Davangere, Karnataka. Today we are going to discuss some aspects of interference of light. Before going to directly the phenomenon, we first discuss what is the basic idea for interference. That is, the principle of superposition of waves. According to the principle of superposition of waves, the resultant displacement due to two or more waves of the same kind at a point is equal to the algebraic sum of the displacements due to individual waves. Here, y1 is the displacement of the particle due to one wave, y2 is the displacement of the particle due to the second wave, then the resultant displacement is given by y is equal to y1 plus y2. This principle is basic for interference. Interference is the phenomenon of redistribution of energy or intensity due to superposition of light waves from two coherent sources. There are two types of interference. They are constructive and destructive interference. In constructive interference, the amplitude of the resultant wave is greater than the individual waves. In a destructive interference, the amplitude of the resultant wave is less than the individual wave. The constructive interference, when crest of one wave falls on the crest of the other, or trough of one wave falls on the trough of the other. Here, the resultant amplitude is high. In destructive interference, the crest of one wave falls on the trough of the other, and here the resultant amplitude is less. This diagram explains the condition for constructive and destructive interference. Here, S1 and S2 are two coherent sources. P is a point on the screen. S1P and S2P are the paths travelled by the two waves, and S2P minus S1P is the path difference between the two. If the path difference is an integral multiple of wavelength of light, the point P is of maximum intensity. If the path difference is odd multiple of the wavelength, then the point P is of minimum intensity. Hence, the interference pattern consisting of bright and dark bands, and they are called fringes. Let us discuss the conditions for sustained interference. To produce continuous and uninterrupted interference pattern, the following conditions must be necessary. The first one is the sources must be coherent. Second one is the sources must be narrow. The third one is the distance between the sources must be very small. Here we mentioned the coherent sources. What are coherent sources? Two sources are said to be coherent if they emit light waves of the same frequency, nearly the same amplitude, and are always in phase with each other. And if we take two independent sources, are they coherent? No, they are not coherent because the phase difference between them is not constant. Then how do you produce the coherent sources? There are two methods to produce the coherent sources. One method is it involves one real source and the other virtual source formed by that real source. Example of this one is Lloyd's single mirror. The second method involves the two virtual sources formed by a single real source. Example of this is Fresnel's biprism. Let us now discuss about the classification of interference phenomenon. There are two classes. The first one is division of wavefront and the second one is division of amplitude. In the division of wavefront class, the wavefront is divided into parts by using mirrors, prisms and lenses. The separated wavefronts travel unequal distances and finally brought together to produce interference. This class requires point source or a narrow slit. Examples are Lloyd's mirror and Fresnel's biprism. The second class is division of amplitude. In this class, a single beam is divided into two or more parts by partial reflection or refraction. These divided parts travel different paths and finally brought together to produce interference. It requires broad light source of high intensity. Examples are interference in thin films, Newton's rings, Michelson's interferometer, etc. Now we will discuss the theory of interference in thin films. What is thin film? A transparent layer having thickness of about few micrometers is treated as thin film. In the thin films, interference phenomenon is due to multiple reflections from the surface. Newton and Hooke observed and developed the theory. Thomas Young explained this phenomenon on the basis of interference between light waves reflected from the top and bottom surfaces of a thin film. In thin films, interference takes place due to reflected light and transmitted light. Let me discuss the theory of interference due to reflected light in thin films. Here we consider a film of thickness T of refractive index mu. In the diagram, SA is the incident wave, AT is the reflected wave from the upper surface of the thin film, AB is the refracted wave, BC is the reflected wave from the lower surface of the thin film, AT and CQ are the two reflected waves from the upper and lower surfaces of the thin film. Draw CN perpendicular to the line AT from the point C and also draw AM perpendicular to the line BC from point A. In the triangle ANC, the angle ACN is I, and in the triangle AMC, the angle CAM is R, where I is the angle of incidence and R is angle of refraction. And AE is produced to meet the point P and then join the line PB. The path travelled by the first wave is SA plus AN plus NT in the air medium, and the path travelled by the second wave is SA in the air medium, AB plus BC in the denser medium plus CQ in the air medium. But NT is equal to CQ and SA is common to both the waves. Therefore, the extra path traveled by the first wave is AN in the rarer medium, and the extra path traveled by the second wave is AB plus BC in the denser medium. The optical path difference between the two waves is given by x is equal to mu into AB plus BC minus AN, and in the triangle ANC, sin I is equal to AN by AC, and in the triangle AMC, sin R is equal to Cm by AC. And from Snell's law, we know that mu is equal to sin I by sin R. It is given by AN by AC whole divided by Cm by AC, and it is equal to AN by Cm, or is equal to mu into Cm. Therefore, the path difference x is equal to mu into AB plus BC minus mu into Cm. Here mu is common, therefore x is equal to mu into AB plus BC minus Cm. But from the diagram we have AB is equal to BC and it is equal to PB. Therefore, path difference x is equal to mu into PC minus Cm, and it is equal to mu into Pm. In the triangle APM, cos R is equal to Pm by AP. Therefore, Pm is equal to AP cos R, and it is equal to AE plus EP cos R. But AE is equal to EP and it is equal to T. Therefore, we have Pm is equal to 2T cos R. Substituting this in the above equation, we get Pm is equal to AP cos R, and it is equal to 2T cos R. Therefore, x is equal to mu into Pm, or the path difference x is equal to 2 mu t cos R. This is equation 1. But in case of reflected light, the equation 1 does not represent the correct path difference, because when light is reflected from the surface of an optically denser medium, a phase change of pi or a path change of lambda by 2 occurs. Here, the first wave undergoes a path change of lambda by 2. Hence, the correct path difference is given by x is equal to 2 mu t cos R minus lambda by 2. Then let us discuss about the conditions for bright and dark fringes. If the path difference x is equal to an integral multiple of lambda, that is 2 mu t cos R is equal to 2n plus 1 lambda by 2, we get bright fringe. Or if the path difference x is equal to 2n plus 1 lambda by 2, or 2 mu t cos R minus lambda by 2 is equal to 2n plus 1 lambda by 2, or 2 mu t cos R is equal to n plus 1 lambda, or it is equal to m lambda, we get dark fringe, where m is an integer. These are the conditions for bright and dark fringes in case of the interference in thin films. These are some basics of interference of light. Dear students, I hope you are benefited by this video. Thank you for watching.